Hello everyone, my name is Xinwei Ding. Today, I and my partner Ling Xiaowang will introduce robot position control based on robot local sensor and neural network. Here is our introduction. First, I will introduce RoboCup robot control system. And then I will talk about the two errors on robot position control, delay time and robot sleeping. And then I will introduce the robot local sensor to deal with delay time. And my partner will introduce neural network to deal with robot sleeping. When robots need to cooperate with each other to finish a task, typically their commands are sent by a host computer. RoboCup robot is a good example to study this kind of control. So let me first introduce its control system. We can see that there are 5 robots in each team, and the central computers will control the robot by using the camera's overfield. This is the whole control processing. We can see that firstly, the camera will take the image and send it to computer. After calculation, the computer will find a control strategy and send the command to robot. Finally, the robot takes the action. All these parts will create a delay time. Although they are very small, when they sum up, it will create a big error to robot position control. There are 2 major errors in this type of control. Delay time is caused by control loop in the former slide. The robot sleeping is caused by some realistic problems, such as robot wheel structure and robot movement style. Let's first see some consequences caused by delay time. In this figure, we can see that at T0, the camera grabs the image with the robot being on the left-hand side of this figure. In the meantime, the central computer will process the robot position. When the image processing is finished, the robot has moved forward to a new position at T1. But at this time, the robot still doesn't receive any stop command, so it continues goes forward. Finally, at T2, when the robot receives the stop command, the robot stops at another position, which is on the right-hand side of this figure. So in this example, although the command is let the robot continue moving forward to chase the ball, but actually the robot has already touched the ball. So as a result, the robot will miss the ball or kick the ball to an unknown direction. Here is another consequence. The robot's behavior is always faster than command. When the robot has already reached the target position because of the delay, the command tells the robot to continue to move forward. As a result, the robot will stop on the right of the target position. And then the robot tries to go back, but also because of the delay. It will stop on the left of the target position. So the robot actually will oscillate around the target position. Another error is robot sleeping. Let's first talk about the robot model in RoboCup. We can see that it is an omnidirectional drive robot, consists of 3 wheels, and the adjacent 2 wheels have 120 degrees with each other. But it has a drawback. This kind of wheel structure will create less friction than normal 2-wheel structure. This will make the robot more easily to sleep, and as a result, the robot leaves its pre-calculated moving path. Now I will introduce robot local sensor and using it to deal with delay time. Local sensor can get the current robot position data and store the data on robot, and using this data to compensate robot position. First, we must know the exact delay time, and a test will deal with this thing. In this test, the robot will receive a signal and move back and forward around the position. From the test data, we can see that when the robot is on the position 101, the camera grabs the image and sends it to computer to process. In the meantime, the robot continue move to position 98, 95, and 78 until the robot moves to position 19. The command position 100 is sent. So actually, it delays for 7 control loops, and this total time is up to 234 microseconds. This picture shows how to use local sensor to compensate the robot position. Every control command will add a compensation value. This compensation value is calculated according to local sensor data, and their sum result will control the robot. In the next, my partner will introduce neural network to deal with robot sleeping.
In this part, I want to introduce the application of neural network in robot position control. As we all know, in real world, sleep and friction should be taken into account when you control the robots. Backpropagation learning algorithm is one of the applications of a neural network, which can solve those problems caused by the sleep and friction. Here is an artificial neural model. This model assumes that the incoming signals and outgoing signals may have only values 0 and 1. If incoming signals summed through the positive or negative weights have a value equal or larger than the threshold, then the neuron output is 1. Otherwise, it is set to 0, while t is threshold. Net value is weighted sum of all incoming signals. Here is an example. The input is 1, 0, 1, and weights are 2, -1, 1, and thresholds are 2. So net equals 1 multiplied by 2 plus 1 multiplied by 1 minus 2. It's positive, so the output is 1. A learning algorithm is an adaptive method by which a network of computing units self-organize to interpret the desired behavior. This is done in some learning algorithm by presenting some examples of desired input and output mapping to a network. A correction step is executed interactively until the network learns to produce the desired response. The learning algorithm is a closed loop of presentation of examples and corrections to network parameters as shown in this figure. The backpropagation algorithm looks for the minimum of error function in weight space using the method of a gradient descent. The combination of the weights which minimize the error function is considered to be the solution to a learning problem. Let me show how backpropagation works. This is a 2 hidden layer network. We get input x, y, z, and we want output be a, b, c. But right now, according to this structure and weights, the output will not be a, b, c. So we should change the weights to get the right answer. First, we calculate the output based on the original network. Then we calculate these are the errors. Then we find the right weights. Here is an example. Here there is a very important parameter. Is learning concept alpha. This parameter determines how fast you can get right answer. when you set different value of a learning constant, the number of loop is different. Here is an example of how backpropagation learning algorithm apply in robot control. This is the separation of actual feed-forward network. As we can see, when the robot get input, and input go into the feed-forward network, and we get output, and output going to the PC to calculate the errors, and we're using the backpropagation to get the new weights. And new weights going to the feedback forward network, and this this is configuration consider 3 robot position labeled global, offset, and target. The first robot corresponds to the position as provided by image processing system. It's the global, and the second position is called offset, corresponds to the robot's true position, and hence includes the travel distance during the time delay. The third robot symbolizes the robot's target position, as already mentioned before. The neural network estimates the robot's true position from the target position, the robot's previous position, and its travel distance. Right now, we want to know how backpropagation algorithms work in robot control. So, we set the learning constant equals 0.1 and compare the performance of our 9 different feed-forward neural network architecture. The results suggest that a network with 5 hidden neurons in one layer yields the best answer. This figure compares the average position error without feed-forward network to that with the feed-forward network stimulated on PC and on robot. Feed-forward network provides a gain over 50% in accuracy. The error caused by the modification of the feed-forward network on robot is not larger than 8%. Here is the second measurement test. The robot divides a specific path that looks like a horizontal 8 and rotate his own axis. This result shows that the local wear sensor impacted on robot advanced accuracy of movement control, but wear sensor cannot measure slip and friction effects. Backpropagation network can reduce the position error caused by these effects. Conclusion. Using the control software analyze images sent by 2 cameras and drives appropriate control commands to the robot, cause time delay at different stage, which leads to the enormous robot behavior. Local sensor compensate for those effects. However, the drives used by most of the research team exhibit certain inaccuracy due to 2 physical effects called slip and friction. Neural networks are able to significantly improve the robot's behavior with respect to accuracy, drive, and response. Thank you very much.